Okay, welcome all back. We are then starting the third day, the lab session with Aurora Caselli. Thank you very much for being here. Thank you, Aurora, and the space is yours.
Okay, great. Thanks so much. Yeah, so today for the lab, we're going to try to do 2 exercises, and we'll see if we get through them both today, but I'd rather go slowly and make sure everybody gets through the first one, and then we can always do the second one tomorrow. So we'll see. Anyways, so for the first part of the lab, we're going to be comparing 2 stars of different spectral types at high resolution. And so the spectra that you are going to need are on the GitHub page. And let me share my screen so I can show you exactly what you need. Okay, so here is the worksheet that we're going to be using for today. So we'll start with this first part. And the spectra that you need, you can download from the GitHub link. So I will show you. Okay, so here's the GitHub page that I put all the spectra. So for the first part of the lab, you're going to need these 2 spectra here that are both, they both start with ADAP, ADAP 2014 and ADAP 27, sorry, ADP 2014 and ADP 2017. For the rest of the lab, I just call them by 2014 and 2017. So you need to download both of these spectra. And you might as well, while you're at it, for the second part of the lab, we're also going to be using this WASP-33 model and this WASP-33 spectrum from Carmenes. Okay, so you need to download those. And then we're going to be using Colaboratory like we did in the first workshop. So if you need help opening the files and all of that, you can use this Colaboratory. You can look at this Colaboratory link about how to open the files. So these are the HARPS files. So you should be looking at the, or I'll just show you. Oops. Okay. Great, yes. So these are the HARPS. For the first part, we're using the HARPS files. So you want to follow from here down. So this is this ADP 2017. This is one of the files we're going to be using. So you can use this exact procedure to open up this ADP 2017 file and ADP 2014 file. So yes, use this exact procedure for those 2. And then we can just plot the 2 different spectra, and then on the worksheet, it'll ask you some questions for comparing those 2. So I will, please let me know if you have any questions or if this isn't clear. But for now, if you don't have any questions, I'm going to turn off my microphone and turn off my camera so that you can work on these 5 questions together. And yeah, I will let you go for maybe 30 minutes, and then we'll come back and answer the questions together. I think that, yeah, with 30 minutes, that'll give us enough time to have like 15 minutes at the end to answer the questions together before the next break. Okay, so let me stop sharing. And if you do have questions about how to open the files or how to do any of the questions, let me know in the chat and I'll come back. But for now, I'll turn off my camera. So I was going to come back in just 3 more minutes, but I was wondering how everybody's doing. If you need more time, it would be great if you could comment in the chat that you need more time. Or if you're ready, I'll just assume you're ready if you don't comment. So if you do want more time, if lots of people want more time, I can wait 5 more minutes or something.
Hi, Aurora. They are asking for 5 more minutes. You're almost
That's
at least the
fine.
person that commented.
Okay, yeah. 5 more minutes is fine. So I'll just wait 5 more minutes and we'll still have plenty of time to for me to explain before the next break. Okay, so it's been 5 more minutes. So I think that we'll go over the answers so that before the next break, we'll finish going over some of the answers, and you guys can ask any questions that you have, and I can, we'll see if we have time to explain the next part. So I'm going to be working in a different co-laboratory notebook, and I'm going to share the link with you. Well, I'll share it with Esteban and he can then share it. Okay, so he will put that in the chat so you can follow along in my co-laboratory notebook. Okay, so let me share my screen, and I've uploaded the files.
Hi, Aurora, you have a question in the chat.
Okay.
Why is the flux in some spectra has negative values?
Okay, yeah, that's a good question. So you would never expect negative counts anywhere you're counting photons. But of course, when we're doing the reduction process, we do some things that can cause our counts to go negative. So for example, if we overestimated the dark current in a pixel, and then we subtract out the average dark current, we can subtract too much if there's very few counts in that pixel anyways, and we would get a negative pixel. And so a negative count in that pixel. So yeah, in some places where there's very low flux, so there's very few counts to start with, some of our correction processes can cause us to get negative counts. But it shouldn't happen anywhere that you have high signal to noise. It can happen in places where you have low counts to start with. Okay. Great. Let me share my screen. Okay. Great. Yes, here is my co-laboratory notebook. And just to save time, I already uploaded the files using the same procedure that we used before. So here I have the 2014 file that I've uploaded, and then uploaded the 2017 file. And then I have labeled them as F2017 for the 2017 file and F2014 for the 2014 file. Okay, and so then I did just do some of the plotting myself, but I'll go through what I did here. So to start for the plotting, yeah, this is the same as before. So you import matplotlib, and I've imported NumPy since I'll use it later. And we saw from before that all of the HARPS data is stored in the first FITS file extension. And the wavelength data is labeled wave. And they've stored it in kind of a weird way where we have to access the, they have an array within an array. So we have to use this 0 to get the array within the array. And then I've plotted that against, so the wave is on the x-axis and the flux is on the y-axis. And I've just made this color blue, and I've made it semi-transparent so you can see when they overlap. And I did the same thing for the 2014, except for I made this one red, and I've labeled it 2014. And if you're not familiar with matplotlib, you can make some really nice plots. So this is kind of just basics of how to add a legend and how to add labels to your axis. So I've labeled the axis in wavelengths in the x-axis and the y-axis counts. And so probably where the person who asked the question asked about negative flux is over here. And we can see that the red spectrum does go below 0. And this is just because there's so little flux in this wavelength region for the red spectrum. And so by doing some of the corrections, we actually get a negative count. Okay, and then to be able to see both of the spectra a bit better, I did the same thing, except for I divided both of the spectra by their mean. And when you're looking at this HARPS data, at first I just tried to divide it by the mean, so using numpy.mean. But what I got is I didn't get any, the spectra just completely went away when I tried to plot this. And the reason this is often true is because the HARPS data or any other high resolution data will have nans. So nan means not a number. And when they, for example, have a pixel that they've masked out because there's some weird detector issue or something that they've noticed that's not correct, instead of putting in a value or interpolating over those values, they'll just put in not a number in the pipeline reduction. So you'll notice that some of the values have nans, and if you just try to divide by the mean, you're not going to get anything. So you have to use, NumPy has a built-in function. It's called nan mean, and then it'll ignore all of the nans. Okay, so now I have my two spectra here, and they're both just normalized, so the y-axis doesn't really mean anything physical anymore. So let me flip back over to my questions and see what we can look at now. Okay, so just looking at the stars, can we tell anything about the effective temperatures? Okay. So for the star that's plotted in red, this is the 2014 star, you can see that we get a lot less flux in the blue. And as we go to the redder wavelengths, we get more and more flux. Whereas for the 2017 star, you get a decent amount of flux in a decent amount of counts in the blue. And then you start to decrease in counts. You hit a maximum and then start to decrease in counts. So there are, again, two effects happening here. One is the edges of the spectrograph are less efficient. And so you're always going to get less counts on this edge and on this edge. But it's the same spectrograph. And so for both of the spectra, you're going to get less counts here and here. But we can clearly see a difference where the 2014 spectrum has a lot more counts in the red than the 2017 spectrum. And so just thinking about black body flux and black body radiation, a star that's cooler is going to emit more at redder wavelengths, and a star that is hotter is going to emit more at bluer wavelengths. So just by this very basic test, we can say that the 2014 star is a cooler star than the 2017 star. So hopefully that makes sense. So now I wanted to look at a few different lines. So I'll just zoom in on my spectra to some different lines and see if we can see these lines in either of these stars. And hopefully this will also give us some more hints about what the spectral type is of these stars. Okay, so I'm just going to rerun this, except for I'm going to limit the x-axis to certain values. So I've looked up on my own on Google what the wavelength of these values are. So we'll start on the blue side. And the calcium H and K lines that I asked about are at 3,875 about to 4,000, somewhere around there. And I'll just label this so you guys can see it later. And since the spectrum is so much lower there, I'm going to also zoom in on the y-axis. Okay, and let's run this. Okay, cool. So we can clearly see two large features in the blue spectrum. We have this kind of doublet absorption here. And so the blue, this is the calcium H and K line. These are singly ionized calcium lines. And these are very prominent lines in the sun and other hotter stars. And you need the star to have a pretty high temperature in order to see the calcium H and K lines, because they result from a singly ionized calcium. So they have to be hot enough to ionize calcium once in order to see these lines. Okay, so next I'll just leave this here so that you'll be able to see it later, but we'll zoom into a different region. So next we'll look at the H alpha. So that's hydrogen. And this is at 656 nanometers, so 6,500 to 6,600. And there's more flux here, so we'll go higher. Okay, so now here we see the 2014 spectrum, and here we see the 2017 spectrum. And we're looking for a line at 656 nanometers, 0.3 technically. And so we can again see this deep line in the 2017 spectrum, which is caused by hydrogen absorption. And if you remember from our lab today, or sorry, from our lecture today, the deepest hydrogen absorption occurs around 8,000-ish Kelvin. So again, this is another hint that the 2017 star is a hotter star. Something maybe around, 8,000, 5,000 to 8,000 Kelvin. We'll kind of see hydrogen emission. Okay, and then the last thing that I wanted to show you, I didn't ask you to look for this one, but I noticed that they both had this, so I thought that this would be interesting. So I'm looking at the sodium doublet here. Okay, cool. So you see a doublet both in the 2014 spectrum and in the 2017 spectrum. And the wavelengths are not quite lined up, but we do see a doublet in both of these. And so it's kind of interesting that we can see this doublet feature in the hotter spectrum and in the cooler spectrum. Okay. So let's go back here. So we looked at some of these lines, and by seeing which elements were in some of these atmospheres, this gave us insights into what the temperatures of these stars are. And then one more thing to give us another insight into the temperature is I just wanted to zoom in really close to a small region. And I just chose this region at random, but most regions would do. So I said 5750 to 5770. Okay, so now we're looking at a very small region, and you can see a difference between the spectra. So the blue spectrum, it seems to be relatively flat, and then you get a few prominent dips like this, relatively flat, a dip. Whereas the red spectrum, it seems to be kind of all over the place. There's just these large dips everywhere. And again, this is just another hint that the red spectrum is cooler, because when we see so many lines like this, this is usually due to molecules. And so we can say that there's probably molecules in the atmosphere of this 2014 spectrum. And if we zoom into a different region where we can clearly see a band head, we can be sure that we have molecules in the spectrum. And so what's interesting is all of these lines on this 2014 spectrum, it's not noise. Those are not caused by a low signal to noise spectrum. Those are actually all like real molecular features. And on extremely low mass stars, we can't ever even really measure a continuum. So what we're seeing here on blue is a kind of continuum, a black body continuum with some absorption lines built on top of the continuum. But in red, for the very low mass stars, we actually can never really measure the black body continuum because there's molecular absorption at almost every wavelength. And so that makes it kind of difficult to do analyses of line depths, because we don't have a continuum to measure these line depths with respect to.
Excuse me, Aurora, you have a question in the chat.
Mm-hmm.
It wasn't quite clear for me why we didn't see a prominent H-alpha on the 2014 spectrum and what we conclude from that.
Oh, sure. Okay, great. Let me go back to looking at the H-alpha. Okay, yeah, so in the 2014 spectrum, we don't see any hydrogen absorption, whereas in the 2017 spectrum, we do see hydrogen absorption. And I'm just going to go back to my lecture slides to demonstrate why we see this. Okay, so it's again this reason here, where H-alpha is caused by the hydrogen being in the n=2 state and then a transition to the n=3 state. So in order to see H-alpha, you need the hydrogen to be excited into the n=2 state. And the fraction of hydrogen in the n=2 state peaks around 8,000 Kelvin. So at temperatures lower than that, you basically see all of the hydrogen in the n=1 state. So that's what this line is showing. So at temperatures of 5,000 Kelvin, all of the hydrogen is in the ground state in n=1. And it's not until we get to higher temperatures where we get a larger fraction of hydrogen in the n=2 state. But then we can't be at too high of a temperature because then the hydrogen becomes ionized. So yeah, this is by seeing H-alpha absorption here. We know that the temperature has to be somewhere between maybe like 5,000 Kelvin and 10,000 Kelvin, because any hotter and we would get ionization, and any cooler and the hydrogen would no longer be in the first excited state. It would either be in the ground state or it would be in molecules. So maybe in H2 or in H2O or something like that. So that's why we don't see any H-alpha feature in the red spectrum. Okay. So then based on all of this information that we've talked about, I was wondering if you would be able to estimate the spectral type. So because we see this H-alpha line and because we see ionized calcium H and K, and also because we see that the spectrum is peaking at bluer wavelengths, we know that this spectrum has to be hotter. And we probably would guess maybe that this spectrum is somewhere around an A-type star. because we see deep hydrogen lines. And in reality, this is the spectrum of WASP-76, which is a very early F-type star, so just about an A-type star. And so our initial guess of what we talked about today, where A-type stars show strong hydrogen lines, is a good guess for what the 2017 spectrum is. And for the 2014 spectrum, since we see molecular lines and we don't see any hydrogen, and the spectrum seems to peak in the infrared, our best guess would probably be an M-type star, and that would be correct. So this is the spectrum of Barnard's star, which is one of the closest M-type stars to the sun, and it has a spectral type of M5. Okay.
Excuse me, Aurora, you have a question here. It's, how can we differentiate between molecular lines and noise in the spectrum? Will that depend on the signal to noise?
Yes, yes. It is difficult to differentiate between molecular lines and noise, because at this, when I'm zoomed out like this, it just looks like noise, and it could just be noise if this was a spectrum that has a low signal to noise. But I've specifically tried to choose a spectrum with a high signal to noise, so there shouldn't be that much noise. And a good way to check yourself is to try to find any, let's zoom out. Okay, yeah, so a good way to check is either to find a place where you know that there's going to be a molecular band head, or a place where you think that there should be strong elemental absorption, because there we should see a single strong line, and you can kind of check to see if the signal to noise ratio looks to see how much noise you would get. But yeah, this is just something that it takes a bit of practice and looking at a lot of spectra to try to see if you're seeing noise or you're seeing molecular lines, because they can look very similar. Okay. That seems to be the questions. And then, the last question I asked is, does it seem like telluric absorption has been corrected for in either of the spectra? So now that we've decided that, a good way to check for this is, now that we've decided that the 2017 spectrum has to be from a hotter star, we shouldn't see any molecular absorption, because molecular absorption only happens in cooler stars. So if we see molecular absorption, we can assume that this is from Earth's atmosphere. I have looked at these spectra a lot, so I know that there's often a molecular absorption band over here. So let's check to see if, that looks like it's in the hot spectrum. Let's see, 6002. 6900. Okay, and we'll zoom in even more. We'll do 68. Okay, great. And so maybe even more. Okay, so in our hot star, which is the blue spectrum, you can clearly see that this doesn't look like atomic absorption. This is the clear band head that I've been talking about today, where you see an initial line and then lots of lines equally spaced. And so since this is a hot star, we don't expect there to be any absorption from molecules. And so this means that we can check in our spectra to see if they've been corrected for telluric absorption. And here we can tell that they have not been corrected for telluric absorption. And so this is a oxygen. This is the O2 band head. Oh, and it looks like I have run over. So let me stop sharing. So let me know if you have any questions for this section, and then I think that we'll take a our 15-minute break, and then we'll come back and I'll explain the next section. And I don't think we'll fully get through the next section, but that's okay. We can pick it up tomorrow during our problem-solving class.
Okay, perfect. Thank you, Aurora. We don't have more questions right now on the chat, but if we have more, we can just write them down and ask Aurora in our next section. We'll see you in 10 minutes, if it's okay for you, Aurora.
Yeah, 10 minutes, that's fine.
We will remain on schedule, so 11:30 here in Colombia, 5:30 your time.
Great.
See you in a while.
Bye.